Okay, so now we're going to discuss more about LU decomposition. Okay, so the last time we talked about using Gaussian elimination to obtain, it's like this LU decomposition, right? So last time discussed how to use Gaussian elimination to obtain a decomposition of some matrix A. It's like into the product of a lower triangular and upper triangular matrix. And so let's talk about how you can then use this to solve a linear system of equations. So solving AX is equal to B. Okay, so the first thing you do is you compute this LU decomposition. And then, of course, that means that instead of AX is equal to B, right, I can substitute A is equal to LU. So this gives me LUX is equal to B. So the first step is to invert essentially the left, so the lower triangular matrix. So I can solve Ly is equal to B for y using forward substitution. Okay, and then once I've done that, okay, I can solve ux is equal to y, right, for x. And I can do this using backward substitution. Okay, so essentially what I'm doing is that I'm thinking of this u times x as y. And so I first solve for L times y is equal to b using forward substitution. Because L is lower triangular, so I can use forward substitution. And then once I have that, I can solve ux is equal to y based on the y I first computed here for x using backward substitution. Okay, so so let's think a little bit about how many operations it's like this takes. Okay. Okay, so let's say that A is a n by n matrix. So let me just sort of make the following observation that LU decomposition, so LU decomposition takes about 2/3 n cubed floating point operations. Okay, and the point is that if you were to compute A inverse, sort of that's more expensive. It's roughly about twice as expensive. Okay. All right. So in order to do this full solve, it's like we have to do this LU decomposition, which we know now takes 2/3 n cubed floating point operations, and then we have to do this forward and backward substitution. Let's see how much those take. Okay. So for the forward substitution, we have L is this lower triangular matrix, which is an n by n matrix. Okay, so the area of the triangle is 1/2 n squared. And then for each entry, we need 1 multiply and 1 subtraction. the forward substitution code. Okay, so roughly, so we need approximately n squared operations. Okay, and the same thing for backward substitution, that's also n squared roughly, right? So backward substitution by sort of essentially the same argument sort of takes n squared flops as well. Okay, so the total cost is sort of 2/3 n cubed plus 2n squared, right? And then this is compared to 4/3 n cubed, right, for computing A inverse, all right? But let's think about it for a second, right? Because you take 4/3 n cubes operations to compute A inverse, but if you compute A inverse, you still have to do this matrix vector product in order to actually compute, it's like the solution, right? But you still have to do a matrix vector product. Right, to compute x as A inverse times B, right? So so that adds some cost to it, right? So you basically have an n by n here, then n by 1, right? So you take roughly sort of 2n operations. Well, you basically have n operations for every row times column. Right? So if you have to take this times this, that's n operations, but that's for every entry, so that's still n cubed, right? So yeah. So this is of the order of n cubed flops just for the matrix vector product, right? Because this n by n, this A inverse is sort of typically full rank. I'm sorry, it's usually a full matrix, right? We don't necessarily assume that it has any sparsity pattern at all, right? And then again, that's like the right-hand side. So this would be A inverse, and this would be B, right? There's sort of nothing. It's like, sorry, that's not what I want, right? The n squared flops, sorry. Yeah, so it takes roughly n squared flops, it's like to do this matrix vector product, okay? Right, because there are sort of n entries, it's like for the vector, it's like, and then each of those n entries takes about n operations, it's like to compute, right? We're really 2n, I guess. Okay, so roughly 2n squared flops. So, so the total cost here is about 4/3 n cubed plus 2n squared as well. Okay, so so you do, I mean, it's like, so the actual per solve cost once you've computed either A inverse or computed LU decomposition is roughly the same, 2n squared versus 2n squared, right? But you save, it's like in LU, it's like in terms of how much it costs to compute LU, the LE decomposition versus its like A inverse. Okay. All right. So so let me just stop here for now.